So Professor Wiart, he's a PhD, of course, and engineer in telecommunication. And since 2015, he has been the holder of the chair of the Caractérisation, Modélisation et Maîtrise of the Institut of Means in Paris, Telecom Paris. And since 2018, he's the president of the Comité d'orientation de l'Observatoire des ondes of Paris. And he's also the chairman of the TC 106 of the European Committee. So this is Senelec, who is in charge of electromagnetic field exposure. And he's actually the president, the chairman of the International, of Commission K, I believe, of the International Union of Radio Science. And he has been the chairman for the French chapter of Ieee. So he's also an emeritus member of the Society of Electrical Engineers since 2008, and a senior member of the IEEE since 2002. So his research interests are, let's say, various, but among them, the experimental numerical methods, machine learning and statistics applied to dosimetry and electromagnetics. And he has been authoring more than 150 publications in journal papers and more than 200 communications. So Professor Wiart, the floor is yours. Thank you very much.
Okay, thank you very much for this kind introduction. First of all, I would like to thank all the people who are attending this workshop. When I discussed with Chaire, and I propose to perform an overview of what has been done since about 30 years, because I am in the domain since about 30 years, and to see what has been done, what were the challenge, but also what are the present challenge. So that means that I will start with a short introduction. You will see that all my presentation is mainly dedicated on the RF exposure and linked to the communication. And so I will not go into the medical application, and I will just cover the method and the challenge to assess the exposure in tissues. So I will define what is EMF exposure, because I think that it's important to define this. And after that, I will explain what has been done. In 30-35 minutes, it will be not exhaustive. That means I will just focus on some aspects. So I will describe what I did and what people did on the numerical and experimental methods dedicated to EMF exposure. And after that, I will cover all the statistical or machine learning method, or hybrid simulation and measurement that are dedicated to overcome the limits. And I finished with a short conclusion. So the idea is, as requested, to go as short as possible in order to leave time for questions, because I think what is also important in this kind of seminar, we are not a lot, and so it's important to have an interactive discussion. So when we look at the wireless communication, whatever is the place over the world, this wireless system are intensively used. So that means that when we look, I put some data for the French people. I think it's about when you are between 15 and 29, it's about 100% of people who are using. And it's not only holding the phone, but it's also the use for personal call, but for watch the internet and to send some information, to get information. It's really an intensive use. And recently, it was 2 years ago, to maybe more, yes, 4 years ago, in 2016, Ofcom, it's from UK, they performed a survey of what are the child that have a phone and what how is the usage. And as you can see, when we are dealing with 12, 15, the number of people, of children having a phone is very, very important. You have more than, some things like more than 86%. So it means that it's a real question, and we have to face the question, and it's part of my research in Chaire. It's part of the debate, but it's also a part of the question that we have in Commission K. In Ieee, the idea is not to focus only on health effect, because we can also look how to use EMF in imaging or in treatment, but it's part of the question. And we have at this time a large debate, at least in Europe, we have a very large debate on is it safe or not. For instance, yesterday, the French the sanitary agency has output another report dealing with the 5G. Is it dangerous? And so they analyze all the literature and they try to give another view or to give a sentence, a summary of what has been done. So as we have now, this question is really a big concern. And of course, I will not spend a lot of time, but the risk, is it a risk or risk perception? But in any case, what we have to do is to assess the exposure, because whatever is the risk or risk perception, people want to know what is the exposure, and they discuss about the exposure. So nowadays, what we have to assess the human exposure in radio frequency, I do not cover the low frequency. So we have to perform this for biomedical study, because when we test the mechanism, or when you analyze the possible mechanism, is important to be able to control the animal or cell exposure in order to have a strong, to be able to have a strong analysis of the organ exposure in order to be able to conclude some things, or to conclude that a mechanism exists or does not exist. But the question is really, if you have a bad dosimetry, your biomedical study will have no good result. You will not be able to deduce anything. So it's not the fundamental, because when we are looking for possible mechanism, people say, okay, it's biology or it's medical. Yes, the medical aspect is very important, but if you perform a bad dosimetry, you will not be able to have a sound result. It's the same for the epidemiological study. It's I'm more involved in epidemiological study than in biomedical study. So the question is really, for instance, to monitor the actual parameter and the relative organ exposure. That is fundamental to analyze the possible correlation. If you perform an epi study without well-defined, and if your dosimetry is not well defined at the beginning, your endpoint for the epi study will be not well covered. Same thing. So that means that we have to design, set up exposure to perform some biomedical study, but we have also to define the protocol or the method that you will use to define the actual emitted power by device. And I think this is important for risk assessment. And dosimetry is also important when you want to design a system. You are not able to design a system now if you do not check the exposure itself, because this in Europe, when you want to put on the market some some communication device, you have to prove that this system is compliant with some guideline. In Europe, it's clear guideline. So that means that we have to define the method to check the compliance. So at each case, it depends. If you say a compliance test, if you want to check the exposure, that means that you will not, the big trouble is not on the time variation. It should be more, it was more on what is the maximum. But if you know, if you have now a new system, you will see that this system play with power, spectrum, throughput, and time variation. So that means that you have to average. So in this case, the compliance is not the maximum of the power emitted, because the maximum can be much higher than the mean value. And what is important is to control, to monitor the mean value. In all the cases, what to say is the numerical and experiment tools are needed. So I will now go more in the method itself. As you know, we have a very wide range of numerical methods that we can use. We can use the volumic approach, that is more or less our FDTD, FIT, TLM. I will go back on this term, but it's mainly you divide your volume in a small cube for FDTD, or small volume with the finite integrated techniques, or with the EFM, you have to define tetrahedric. So this is volumic. And after that, we can have the Mon method. This is quite often used in some other, it's antenna design and something like this. And when we are far from the source in the far field, you can discuss, you can use physical optics or geometrical optics or UTD, uniform theory of diffraction. And so all this aspect is on this case. If you want to know what is the exposure of a given organ, you will not use UTD, you will use FIT or TLM or TLM or FDTD. If you want to cover if you want to analyze what is emitted by antenna, depend on the distance, but you can use moment method if you want, or you can use some other method like physical optics. So we have a large range. If we cover now the quantification of the exposure, the quantification is more or less defined by the SCR. So if we have some question, we can go back, but SCR is the usual way to assess the exposure between 100 megahertz and something close to 2-3 gig. And for the frequency that are above 2 gigahertz, 2 or 3 gigahertz, we are to use the power density. So it's like the Poynting vector. So the main difference is on one side we have the SCR that is more or less used to quantify the watt per kilogram that is really inside, and the power density transmitted. We have to define the watt per meter square. The SCR is estimated usually, as I said, with FDTD and other methods. The main problem that at the beginning, 30 years ago, the main problem was that the head, because the first question was linked to the head, but the body, the human body, is really highly heterogeneous. So we have to use a method that is able to play with this heterogeneity. And at this time, only FDTD was really able to cover this strong non-sparse matrix. So we have used this, and I will go quickly. You have some formula, it's just to show, but this is in principle the principle of the FDTD. But this has been used really intensively from 90 to now. Now we are moving from FDTD to FIT. We have FDTD, FIT, depend on the people who are using. But from the beginning, what is interesting is this is what we did in 95. So I was more or less at the beginning of this kind of research, and Ieee Ramasamy present some update in Ieee proceedings, and as you can see, it was the top of the top. This is the head, and they play with a cube of 5 millimeters. Now this is what we're able to do. We're able to cover millimeter of system, so we are able to handle very fine system. So you see that in 25, 30 years, the problem has really changed. We are not only looking at a layered sphere in front of something that represents a mobile phone, but we are able to design a mobile phone quite accurately. So this is more or less what we can say from the 25 years. We have been able to more or less to control, to define, or to design, to model accurately a phone, and to use millimeters of that, to use body, and we have the body, more or less with a grid of 1 millimeter. So we have been able to look at what is the SAR, the whole body SAR versus the frequency, and we have studied that. We see that at about 80, 100 megahertz, we have some resonances, and at this frequency, that is the frequency close and above 1 gig, you see that small people have higher. It's like a sphere. You can see a sphere. What you receive is proportional to the cross section of the sphere, and the SAR is the ratio of the absorbed power divided by the mass. So if you consider that the absorbed power is proportional to the cross section of the sphere divided by the mass of the sphere, you will have a SAR proportional to the inverse of the radius. Smaller you are, higher will be the frequency, higher will be the SAR. And we had during the 2000 to 2015, we had a very large effort to develop model that can be used by FDTD. And this is, as you know, maybe is a virtual family, but it's not only the virtual family. A lot of effort has been done in Japan, in France, and dealing with the fetus and the pregnant woman, we have been able also to develop specific model. So that means that we have been able to analyze, for instance, the exposure of the peripheral brain tissues, and this is why we built after, because we more or less this figure was used to perform the first epidemiological study, and this was performed just after the big interphone study, and this study has been used for the MobiKid study. So that means it's dedicated to the children exposure, the head of the children exposure. As to the far field, large effort has also been done to assess numerically the exposure, because as you know, in many countries, the question is not so much, the risk is not perceived as important from the mobile phone, it is perceived as important coming from the base station. We know that the exposure induced by a mobile phone is much higher than the exposure induced by base station. You can say, well, if you use your mobile 10 minutes, it's about what you get in 1 month of base station. So you have to look for the duration, but nevertheless, there is a big concern about what is emitted by base station. This is why so many companies propose some tools to design and to inform the public. The advantage and the limit of the computation is, in fact, we take advantage of the GPU. As you know, with GPU, the high computational performance, we change of range. We have much more possibility. I remember in '95 to perform a very simplistic head request days and even weeks. With the GPU, we divide by 40 the time, and we are able to play much more quickly, to run, to have quick run. But if the simulation tools are quicker, the complexity are increasing. The complexity of the ICT is increasing. So to define a mobile phone it's a lot of work. And it's also, ICT is versatile. You don't know exactly in which way, when you look at the actual power emitted, or at least the actual exposure of the brain for AP study, you are not able to give one number. We are not looking at the maximum. So that means that you have to perform. People do not handle the phone in the same manner, and your phone is changing, your apps can change also, and you have to combine all these parameters in order to give the mean value, the median value of the exposure. Yes, but since this ICT is versatile, it's very difficult to use computation alone. So this is why after 2010, we start to use the surrogate model. So in fact, is to say statistics are important to manage variability and uncertainty. What do? Is we just, this is a present paradigm. We consider that we have a deterministic function. LTCI is a deterministic function of a few parameters. But if we look at the real life, these parameters can be what? Okay. These parameters can be the shape of the phone, the shape of the head, the density properties, and from one person to another person, we have some variability. So that means that we have to consider not LTCI or the Y as a deterministic function that we did in the past, but we have to work with a random variable. And so this is the paradigm that we have. We have now LTCI, a function of a random variable. And we are doing now, when we look at this question, we have to say, now the objective has been to build a global framework to propagate and quantify the uncertainty in FDTD, for instance. So first of all, we quantify the source uncertainty, we model, we use FDTD, in fact, and we propagate through the FDTD's uncertainty, and we quantify CDF, PDF as we want. The key question is, how to build the surrogate model, because you want to build something quicker. A resolution, when we play with FDTD, even if the head is the computation of the exposure of the phone close to the head is about say half an hour, 10, between 10 and half an hour. When we perform a lot of run, you will need a lot of computation. Also, we are not able to compute everything. And what we want is to substitute to the FDTD something that is like a surrogate model. We have different models. In this case, we have used in my lab, we have used chaos polynomial expansion. So that means that due to this phenomena, we know that Wiener proof, it's a long time ago, he proved that whatever is this kind of random function, in this case, x and y are not anymore deterministic, they are random function, with a finite variance of for y, and this is what it is written in this case. So he proved that we can expand this variable in a sum of weighted functions. So this is random variable. We have the weighting function, the weighting factor, and this is the basis. It's like a Fourier transform somewhere. So, and so this is a definition. And so the question is, you know the hex because you built it, you know what is the uncertainty, even if you have to normalize and to have some pre-processing for the y value, for the x value, but we know the basis and you know the input. So the question is, what are the coefficient and how many basis I will need to represent accurately the output. So I will not spend a lot of time on this because you can ask questions, but we have very efficient techniques in order to determine the beta, and we are able, depending on the accuracy you look for the exposure, for the SAR, we are able to build a process and design of experiments, so a number of simulations that are able to assess the coefficient. And we applied this for this, and with 100, more or less 100 simulations with FDTD, we have been able to play with a surrogate model, and with the surrogate model, we can do a lot of simulation with a Monte Carlo simulation. So that means that we have more than 100,000 and 10,000, and we are able to play with 10,000, and we built this. And we are not able to have this PDF, and we are able to look at the quantile and to see what is the chick and so on. So, and of course, in this case, the uncertainty where we are using the form, the theta is about 0 and 30. We have the angle like this is plus minus 15. And we have also the location of the phone. So we perform for the EPI study, we perform this kind of analysis, and now we have the PDF. Using this experimental approach, we had a system very easy. We spent about 10 years to define accurately the phantom and the probe to assess the SAR in a liquid. And the liquid is designed to overestimate the SAR. And what we have is a conventional SAR measurement. We have the standardization position of the phone, and we have all the system is now defined in a standard. It's in IEC, it's 62209-1-2-3. And what has been done is they built advanced, because they built advanced SCR measurement system, because one system, one phone, is not only GSM or 3G, is GSM, 3G, LTE, so it can cover a lot of frequency. So that means that when we look at the frequency used by the cellular network now is 700, 900, 1800, 2.1, 2.6, 2.4, 2.6, and now recently 3.5. So all the frequency that have been used by LTE, 3G, Wi-Fi can be in the phone. So you have to test for all these frequencies. So to speed up the test, several systems have been developed. So we have now this kind from ArtFi and from Speak. This is the system that has been developed. And we are now looking at how can we measure the SCR using a non-invasive, because all these systems are more or less invasive. You need to have a probe inside the liquid. So we are working on this. We have a first publication time ago, and we are now looking at this problem of coupling of the phone. Okay, I will spend, because time is running, I will, you will be able to read this. It's how to reconstruct based on the plane wave expansion, as well as the world density. The far field measurement, it's a problem, because the far field measurement, we have a lot of things. It seems to be simple. We can say, okay, you have a probe, you can measure, and you have the result. Yes, so if you want to perform the exposure close to the base station, you can use this spherical mode assessment. So this is a system from MVG. You can measure the spherical mode. At least you have you measure the coefficient, and you can expand this. And after that, if you have the field, you can use the Huygens box, like equivalent principle, and we did it, and it's quite efficient because we have a small box. You have the spherical mode. You can use this spherical mode to perform the incident wave on the FDT in the FDTD, and you can play with the Huygens box to assess the exposure. But in this case, what you will have is you will neglect the coupling between the antenna and the person. Last and final element is now a step ahead. What we are from deterministic, we improve the numerical techniques. We build surrogate model to build some things that is able to look for the variability of posture and usage. But as we know, when we perform the measurement, we have the measurement only at the location where you are dealing the measurement, and we can have some measurement in NFA, but the question is really what is needed now is a map of the exposure, and we try to analyze if we can do the sensor, we can do the RF mapping. We work on this RF mapping using the measurement and the artificial neural network. So when we look at the measurement performed by the French National Agency on frequency, there is a lot. This is a number in rural, urban, indoor, outdoor, and with the number of measurements. And so they perform each year. There is a report, so you can see that we have thousands of measurements. Each year there is about 3,000 measurements, and we have this value. So we can say, okay, we have the mean value, and as you can see the mean value of the compress because all the frequency are taken into account. But anyway, so the equivalent is about 0.4 volt per meter. This is of great interest, but as you can see, they're interested, but they provide information only at one location. So there is a need for RF mapping. So this is why we are working on this aspect. We have a sensor able to record at a given location the time variation of the exposure. This sensor can be developed by XM, it's a company, and we look at the 14 districts of Paris, and we analyze what is the exposure. And if you want, you can read this paper. The conclusion of this paper, it's a recent paper because we published a few months ago. To train, it's only based on simulation. It's the first trial that we did, only simulation, and we just analyze how many sensors we need and what we can do with the artificial intelligence. In fact, what we have is we can consider that we analyze the measurement. We have the measurement by sensor and by drive test, and we can use the location of the antenna, because no one is using this. When we perform measurement, you do not take into account where is the antenna. You can, but you didn't. What you want is to say, okay, I want to be able to perform a measurement in a blind way. Yes, but in this case, you do not use important information that are the frequency used by this antenna, by the antenna, and you didn't use the location of the antenna. So this is what we did in this paper, and the conclusion are the drive test measurement are needed to avoid very huge number of sensors. So this is what we conclude, and so that means that we didn't say that sensors are not useful, because when you plan, when you build a model of your exposure, the question that you can have is when the training is not up to date. You train, for instance, you are in a city, you train your neural network to the measurement you perform in January, and when do you have to restart the training in order to update the model? And so the sensor will be used to control the validity of the forecast. What is abnormal measurement? What is outlier? And what is a change of behavior? So this is what we are now, what we are working on. And this is the abnormal situation. So sometimes you see that we have in this case some abnormal situation, but we can have a change if you consider that in the confinement, for instance, but you can have a different pattern of exposure. So this is the end of my talk, and I give you an overview of what has been done, and I hope that will give you the opportunity to look inside more accurately.